All right, good morning. So I hope everybody had a refreshing spring break. Uh, Fortunately or unfortunately, we need to cover a lot today. And there's quite a bit of things to talk about. Logistically, homework number 5 was, I think everybody submitted homework number 5. There were a couple of emails that I was not able to get to over the weekend and at the end of last week. So I started replying to everyone today morning, but there's few of you that I have not replied still. So I'm quite lenient regarding the deadlines. So if you have any issues, then please email me. I'll try to be as accommodative as possible. That's usually not going to be an issue. The problem is going to happen when we get to the end of the course. So April 22nd is the deadline for project submissions, and that's a hard deadline. The issue there is that Georgia Tech has this policy where we are not supposed to collect anything during the reading period. So your last homework as well as project is going to be, the deadline for that is project paper is going to be, the deadline for that is going to be April 22nd. So on that note, I won't be able to increase or change the deadline for those two things. So just something to keep in mind from now itself. All the other ones, we are quite flexible in terms of the deadlines, but at the end, it is a hard deadline that we need to look at. Regarding exams, so I started grading today morning. So most of it is auto-graded, but I need to go through every single paper to see if there's a few small changes that Canvas has not got. For instance, I discovered today morning that one of the answers is 0.02, but some of you have written it as 0.02, and Canvas has marked this incorrectly. So I need to go back and go through individually and add these kind of points. So those are the only things that is remaining. So I'll go through that. I've started going through that already, but by the end of today, I need at least like 2 or 3 hours. So by the end of today, I'll be releasing the grades for exam number 2. And Wednesday, we can have a further discussion about the answers themselves. And you'll be able to see your solutions as well. So we'll do that on Wednesday. Regarding the new homework number 6, so it has been designed to be worked on the H100 nodes. So these are like top tier GPUs essentially. I believe that each GPU itself is worth like 40K or something like that, and we got them just last month. At least Pace got them last month, and the Pace engineers have been working on it for a while. So for this course, you will have access to it for you doing your project as well as the homework. So we have tried to kind of migrate to the H100s in this new homework. I believe everything is working, but I've not worked on it myself. So Lorraine created this tutorial where you'll be able to go and create instances using the new H100 node. So please try that as soon as possible. Regarding the homework itself, I don't believe it's too difficult. There is one large training module that it will take a little bit of time, but the fact that we have high-powered GPU means that you should be able to do it quite quickly. But if there are issues, please let us know. I'm sure while migrating, there are going to be a few code snippets here and there that will fail, and it'll be good for us to know. And from this homework onwards, there's not going to be like a very fixed result that you need to get. The reason being that there are multiple ways. Like we are giving the baseline or the simplest possible code for you to run, but there are multiple bells and whistles that you can add on top of it. Everything that you see, like just type in neural networks and see the new things for training. There are multiple things online that you can add to your code and get better results. So you're more than welcome to try all those things. So there won't be so if the result, let's say, is supposed to be 70%, but then you can try even simple minor things you can do on top of it in order to get like 75%. So you're more than welcome to try all those things. And of course, the fact that you will have access to H100s means that it will be much easier for you to go through and look at those results. Regarding the project itself, you can also do the same thing, the project on the H100, so you're more than welcome to try it out. I believe Jorge did try it out, like the SAM module itself. He was able to run SAM on H100s a few days back. I'm not sure if he's released that tutorial. If he hasn't, I'll just let him know to create this kind of a PDF of the requirements.txt and send it to everyone so that you'll be able to run SAM module on the high-powered GPUs as well. So that should hopefully help alleviate any kind of issues that you have in terms of computation. You wouldn't have to use your laptops. You could use the PACE cluster with H100s to actually do this. This is different from the PACE ICE cluster, by the way. PACE ICE is still there. If you've used it before, you can continue using it, but this is a different H100, different set of nodes that we have access to right now for the class. Again, I think the tutorial was like, Lorraine released that tutorial. It should be on that folder, assignment number 6 folder. You should be able to go there and check that tutorial out and go through and create all these instances. Again, I urge everyone to do it as quickly as possible because again, the setup, if you have never used PACE before, it might be a bit challenging in terms of getting everything right. But apart from that, it should work well. Yes?
Will there be space issues in PACE?
So they're giving 15 GB right now, but for project, we are asking for a little bit more, so they haven't come back yet. Again, since it was a spring break, there was a little bit of, it was not as much synchronized, but hopefully over the next week, we'll get more space in terms of storage.
Yeah, because in PACE ICE, like when I downloaded some packages, Python packages, like I wasn't able to download any further. It said that it exceeded this space.
Oh, so, in this, I think you have 15 GB.
Okay.
So I do believe that should be sufficient. For homeworks, it is sufficient.
Okay.
But maybe if you do something additionally for projects and stuff like that, maybe there's more required. So we are in the process of getting a little bit more storage. But right now, yeah, it's about 15 GB of storage that you have. Yeah. All right, so last thing. So I won't have an office hours today afternoon. So I'm covering a different lecture on the other side of campus, actually. So I need to be there at 11 o'clock. So that conflicts with the office hours. So I won't have an office hours this week. That also means that I won't be able to stay here after the end of class as well. Maybe we can talk about like shifting the office hours, like maybe on Thursday or Friday, something like that, or we'll have office hours next week on Monday as usual, which also means that I should probably like end a few minutes early, the lecture a few minutes early. So let's try to get as much in as possible. This is a long lecture that is going to cover autoencoders. I believe there are about 60 slides. So before spring break, when we stopped, we were discussing about convolutional neural networks. We talked quite a bit about optimization. One thing that we did not cover was the idea of visualization of what these convolutional neural networks look like. Instead of treating this as a separate part, what we'll do right now is have visualization of CNNs with explainability literature that we will look through next week. But what I wanted to cover within the visualization process, we'll cover it in terms of autoencoders. So it's not going to be too different in terms of what you'll be seeing in terms of lecture. So this is the overview for today. We'll talk mainly about autoencoders and different kinds of autoencoders. Specifically, we'll look at fully connected, convolutional, and within regularized. There's a couple of autoencoders that are there. We'll look through variational autoencoders later on Wednesday. All right, let's start off with something that we have seen before, which is the types of learning part. So the last time we looked at this particular slide, we were transitioning from regression towards clustering. Classification and regression are supervised learning, where not only do you have access to the data, but you have access to the labels as well. The y1 to yn, these exist as well. But in clustering, as you saw, there was no label as such. You had these set of data points that you wanted to cluster within either using k-means or GMMs or any other algorithm, but there was no true labels associated with these clusters, right? So this is essentially what we had in terms of your unsupervised learning algorithms, where you don't have access to these labels. You only have access to the data points, which are x1 to xn. And the goal in this case as well in unsupervised learning is always going to be trying to find this kind of a hidden structure. Except before, when we were looking at k-means and GMMs, this time we'll be looking at neural network methodologies of constructing these unsupervised learning algorithms. And the most important of these methods is going to be your autoencoders. So what is an autoencoder? Very simply put, it helps you learn this kind of a lower dimensional latent representation from unlabeled data. So everything that we saw in CNNs was we had this idea of an input X that as you went deeper within your architecture, you, at the end of the day, you were able to assign a single number to it, which was a class, right? Given a huge image, let's say 1080p image, you were able to take that image and say that if it belongs to a cat class or a dog class. In a sense, you're just constructing a single number out of it. So that is what we talked about in CNNs, where a large image was brought down to a lower representation space, and that lower dimensional space was then used to convert it into a single number. The difference in autoencoders is that we have the same input data, and the middle portion is the same thing. We are going down to a lower representation space. The size of that is going to be less. If this is going to be something like 784 cross 1, you're going to go down to something like 128 cross 1. I'm just giving these numbers as examples, but essentially a large data point is converted to a smaller data point. The difference from, so until this point, it's very similar to a CNN or the neural networks that we have seen. But the difference comes later, where instead of converting that 128 cross 1 into a single number, we are blowing it back up to the same dimensions as what we had started with. In other words, we are reconstructing the same input data X in this X tilde as well. In some ways, autoencoders can be a little bit confusing because their goals are not very much aligned with what we have seen till now, right? So our goal has always been to get this kind of Y, this class out of a neural network. But then now we are saying that we want to get back X. And the reason we want to do that is because we want to learn some underlying hidden structure within the data. And that is going to become more clearer when we talk about the application part of it. So for now, I'll just continue with the autoencoder structure itself. So it is an unsupervised learning algorithm because you don't have access to X. And if you look at the architecture itself, you have, you don't have access to Y, or there is no Y in this particular case. In the beginning, you have an X. At the end, you have an X cap, which is kind of a reconstructed version of your X. So it is reconstructing the data in this unsupervised learning fashion. Now, there are three applications that we are going to discuss with respect to autoencoders, and that will hopefully help you analyze or understand autoencoders a little bit better. The first one is going to be visualization, then dimensionality reduction, and some kind of subsequent supervised tasks that we can do on top of this representation space that has been learned by your autoencoder. So let's talk about the simplest one. The one it was designed for, which is this idea of dimensionality reduction. Now, when we talked about your singular value decomposition, SVD, we had this thing where given some kind of a data matrix, let's just call it a matrix, we were able to decompose into U sigma V transpose, right? Where we had these kind of column vectors and then singular values that were within the sigma, or maybe I should say US, singular values, and then V was the row vectors that, you know, when you combined all these things, you were able to get X. We did not place any kind of a restriction on what X is. But if I were to tell you that X is like a symmetric matrix and X is a covariance matrix of your data, then SVD is nothing but PCA, which is principal component analysis. What PCA gives you is this kind of a dimensionality reduction. Again, you did this in SVD as well. A simpler version of that is the PCA, or maybe not a simpler, I shouldn't say the word simpler, maybe a more restrictive version of that, which has a very specific meaning, is PCA, which is principal component analysis. So given your data matrix X, we can then multiply it with V of K, which is the same as what you had here. We can usually call this as eigenvectors right now in PCA. So when you have these eigenvectors, when you multiply the matrix X, we get a smaller dimensional representation space. So you go from a, let's say, 1,000 dimensional representation space, or I think I'd used 784 cross 1 in the previous one. And you can now go to a 128 cross 1 based on these eigenvectors V that we had. So Vk essentially transforms X to a k-dimensional subspace where k is less than P. This, again, we had seen this in the singular value decomposition. PCA is very, very similar to the singular value decomposition, except there's more restrictions on what X is going to be. Now, if we want to reconstruct back the matrix, you did this in the SVD as well. You took your matrix, you decomposed it, and then when you multiplied using the correct U, V, and S, you were able to get back the exact matrix as before, right? That is essentially what we have in PCA as well, where given a decomposition, here you don't have U and V separately. In PCA, U equals V. So the first one there is U. So U equals V in PCA because of the restrictions that is placed on the initial matrix X itself. So once you have that, you can use this very simple formula where X cap is given by X multiplied by V transpose, and you'll get back the original matrix. Now, the reason we are talking about this is this helps us trying to motivate what an autoencoder is doing. You can think of U S V transpose in singular value decomposition. Your U is multiplying it and converting it into a different representational space. You can think of that as this middle representation space, on top of which you're choosing your singular values, which is going to be S. And when you multiply it again with this V transpose, it brings it back to the original dimensions. So essentially, what we are doing here is trying to understand your autoencoders in terms of what we had discussed before, which is a singular value decomposition. And if instead of giving you a formula where SVD has a formula in terms of pseudo inverse, but if we were to say that I don't want to use pseudo inverse, then you would have to use your gradient descent methodology. You need to construct a loss function and do gradient descent, right? So usually the reconstruction error that we'll use is X, which is your original data matrix, minus X VK transpose, which is essentially just your reconstruction. So you're just taking a norm between X minus X cap, and you're finding your loss. Yes?
Dimension of VK.
Which one?
Dimension of VK.
So VK is going to be, in singular value decomposition when you did it, if you had a 128 cross 128 matrix, your U is going to be something like 128 cross 128, and then your singular values, it could be, 64 cross 64, plus you can pad another 64 onto it, and then your V will be the same size, 128 cross 128. So the resolution itself, the dimensionality is controlled by that S. Right? So you can use that S multiplied by V now to control the value, the dimensionality of your original element A. Maybe the reason this is a little bit unclear is because the way we use U sigma V, in PCA, it's just V sigma V transpose. So it's going to be the same in both cases. The left-hand side matrix as well as the right-hand side decomposition is going to be the exact same in both these cases. So when I mean V, I don't mean this side. I mean either of these two things work in this case. So theoretically, if I was to construct an autoencoder with a single fully connected layer, these terminologies, we're just using the same thing that we had done when we talked about CNNs. So if I have a fully connected layer from the input data to a representation space, something like 128, if this is 128 cross 1, and I want a 64 cross 1, so this fully connected layer is 128 cross 64. if this is my dimensionality, 128 cross 64 of my V, then as long as there's a single fully connected layer and there is a linear activation for V on the left-hand side, and the right-hand side is also a 64 cross 128, it's just the transposed version of the same matrix, right? And then there's also a linear activation. So then your PCA is actually going to be the same as your autoencoder. Again, we are doing all this just so that you can kind of relate. We can motivate this kind of a new neural network architecture based on something that we already know. Singular value decomposition and PCA are like very, very standard signal processing methodologies where given a data matrix, we'll be able to decompose them and convert them into any kind of, and manipulate this data in any way we want. That's exactly what we can do with neural autoencoders as well, which is given this kind of a decomposition, you can think of it similar to what you were in terms of like Fourier transform or inverse Fourier transform, where you can go into a different dimensional space, and within that space you can do any kind of manipulations you want and bring it back to the original the signal space itself, right? This is exactly the same. We're just motivating it using the SVD and PCA algorithm. The difference, of course, is that instead of a closed form solution, so before we saw normal equation, right? So normal equation is not something that we can utilize, especially when the number of features are going to be very large. Same thing in this case as well. So if we need more than one fully connected layer, then we are leaving PCA behind. It's not a linear projection like what we see in the bottom right here, but rather it's going to be a non-linear projection on some kind of a manifold. So in this case, what we'll be using throughout the lecture is essentially non-linear activations between our fully connected layers, or in fact, we can even remove the fully connected layer and convert that into like a convolution layer and so forth. Again, this is more of a motivation to introduce you to autoencoders based on something that you have already seen, which is your PCA or your SVD. The goal is to decompose your data X into some kind of a different representational space in Z, and then use that Z to reconstruct back X cap. And any manipulation that you do within the Z dimensional space can now be re-represented back within your original limit space. Yes?
When we're doing PCA here, does it not recreate X exactly?
It does recreate X exactly. PCA does recreate X exactly, but autoencoders you might not, because again, as I mentioned, your X minus this is like a loss function, and you're using gradient descent plus regularization in order to reconstruct it. So that's why we have X cap rather than call it as X. But again, if it's a very simple framework where you have a single fully connected layer and a linear activation, it is PCA and you'll be able to reconstruct it back. But it's not as informative or useful for us for downstream tasks afterwards. Any other questions? All right, so let's start looking at this in terms of examples. And let's also start formalizing the language that we'll be using. Our input data can be X. Instead of thinking of it as a matrix, X can be a single image. It could be this 1, it could be this 0. And the V that we were talking about before, instead of calling it by a single parameter name, it is basically going to be this encoder. It's going to take your X and it's going to spit out a representation Z based on the X that you have. And that function that does this kind of transformation is going to be called an encoder or an encoder architecture. So what we want from Z is we want Z to capture some meaningful patterns, some semantically understandable patterns within the data itself. So what do I mean by semantic, by the way? So anything that I can provide a language token to. So in this particular case, this 1, I can say that it's basically a straight line. 0, I can say that it's a circle. So there are words in English that I can use to represent or talk about these kind of numbers, right? So a 9 is nothing more than a straight line plus a circle at the appropriate region. So I don't need to know the word 9. I just need to know that there's a straight line and there's a circle, and I need to understand the spatial locality. Based on those two things, I'll be able to reconstruct a 9 right now based on just knowing this and this semantic concepts, right? So the goal of an autoencoder within Z is to learn these semantic concepts so that when you want to reconstruct back the original image, I only trained it with a 1 or 0, but then I'm giving a 9. It will be able to retrain, it will be able to provide 9 later down the line because it has learned the semantic concepts of 1 and 0, which it uses in order to create that 9. So that is what we mean by it needs to capture these kind of meaningful patterns within the data itself. So the encoding architecture is basically something that takes X and gives Z. The decoding architecture or the decoder is something that takes Z and gives us an X cap. For now, we should always think of encoder and decoder that occur together. Where, given your X, you pass it through an encoder, you get a latent representation Z. You can do anything on top of it. We'll talk about what that doing anything on top of it means during Wednesday's lecture. But once you do something on top of it, you can then reconstruct it back and we can get an X cap result out of it. So this encoder plus decoder architecture is what we call autoencoding. And the goal is to reconstruct the data itself. Given X, you will get X cap, and hence it's basically encoding itself within the representation space. And the name autoencoder comes from that. So how would you train something like this? Very simple. Based on everything that you have studied with neural networks, it's exactly similar to that. Given an input data X, given a reconstruction X cap, you're just going to construct this kind of a loss function. The easiest loss function you can find is MSE, which is your least squares error. You can do an X minus X cap norm square. Again, there's no label, so there's no way of us to even use labels. So if this is the image of 0, the output is going to be the same 0, and I need to reconstruct back that particular image, and I'll get back the original thing. So you're training without having access to any kind of labels in order to get your encoder and decoder architectures. Now, the simplified diagram that we were showing before was for let's just say one layer, or it's more of a toy example. But of course, it could be very similar. The encoder decoders could be very similar to what you have seen before. These are essentially your fully connected layers that you had seen. So this is FC1, this is FC2, this is FC3. So if you were to construct this kind of architecture in PyTorch, you would essentially call these kind of linear layers one after the other, with of course some kind of a non-linearity between them, either a ReLU or a sigmoid, in order to construct your architecture. I think I've talked about X. E of theta of X is going to be your encoder. Z is something, I don't think I mentioned this, but Z, the middle layer representation, we'll start calling it as latent representation. So what I just said then, which is the middle layer, is not always going to be true. It's going to depend on your architecture, but the layer of interest or the activations from your layer of interest is generally what we'll call a latent representation. When you want to use this within generative modeling, for instance, which we'll talk about on Wednesday, this is the layer. The outputs of this layer that we are going to be using is going to be called the latent representation. It's nothing more than the activation map from some layer L that we will have to predefine within our architecture itself. So we can call it as our layer of interest, essentially, as the outputs of our layer of interest will be our latent representation. Then decoder is usually depicted using the letter G, and our reconstructed output is going to be X cap in this framework. If you were to use a MNIST dataset, again, it's 28 cross 28, which is going to give you P is equal to 784. P is the number of features. So essentially, you're going to take a 28 cross 28 image, convert it into a vector of size 784 cross 1, and pass it through the network. So the first layer is going to be 784 cross I don't know, maybe something like 256, then 256 cross 128, 128 cross 64, and after that it's you need to bring it back up again. So it's like 64 cross 128 and 128 cross 256. Now I'm writing this as if it's symmetrical. Usually it is. Like when you first construct your autoencoders, it is going to be, you need to make it symmetrical, but then it is not necessary for it to always be symmetrical. It can be any kind of, this could be 128 cross 784, and I can get back the output at this point itself. But it adds a few issues into your training process. Your encoder and decoder will then have to have different, let's say, learning rates, maybe different optimization techniques. So it's not always optimal to do something like that, especially when you're starting out. So think of autoencoders for now to be some kind of symmetric architectures. Later down the line, when you're more experienced in terms of constructing architectures, you should be able to construct non-symmetrical autoencoders as well. Yeah, the network itself doesn't know it's an image at this point because it's a fully connected network. So it just looks at it as a 784 cross 1 vector. There's no spatial similarity similar to what we were doing with convolutions, right? So it's a very simple, straightforward architecture. Yeah, so you have layer 1, you have 128, and of course, I think I forgot to talk about the nonlinear activation. There needs to be a ReLU activation here that goes through and acts on top of your outputs from your kernels. ReLU activations, sigmoid activation in the output layer. So usually what happens is there's different kinds of decoders. We have something called a linear decoder that is used in many applications. The reason being that you have these kind of images. When your images are grayscale between 0 to 255, you have to normalize your image between 0 to 1 and then pass it through the network. Or sometimes what you do is you convert it into -1 to 1. Depending on the kind of images you have, you can convert it into -1 to 1. In such instances, you can't use ReLU at the very end, right? This point, if you use ReLU, anything that is between -1 to 0, you're going to lose it. So you'll never be able to reconstruct back the image from -1 to 1. So you have to be very careful in the kind of activations that you are using at the end of your decoder. You want to make sure that your input is reconstructed. So you need to look at the range of values for your input and make sure that the final activation has that range of values. Sigmoid is usually used because most of the images themselves are always going to be between 0 and 1, and your sigmoid constrains your output to be 0 and 1. If it's ReLU, and this is something like 45, let's say, the output of one of your neurons, the output at the end is also going to be 45. But then if you have a sigmoid, your 45 is flattened down to 1. So generally, decoders, it's better to have either linear decoders or sigmoid decoders. Again, I'm only talking about the final layer. So in between, it's fine to have ReLUs within the decoder as well. It's just that the final output should not be acted on by ReLU. Generally, it's better to have either linear or sigmoid functions over there. All right, so this is like the input and reconstruction. When we train this architecture on MNIST dataset, you can see, maybe I'll show this first. Yeah, you can see it. All right, so the input is something that you see here, and this is the reconstructed outputs. As you can see, there's a little bit of difference. There's a reconstruction error that exists. Your mean square error is 0.0677. This is a very small error, and yet you should be able to make out the difference. Like it's more blurrier here compared to the original input, right? So there is some kind of a reconstruction loss. Your network has not been able to reconstruct exactly the images that it had seen before. This is when I had a linear activation function, so that basically means that there is no ReLU. It's all just a linear layer at every single instance. But if I do have a nonlinear ReLU, then this is how the output is going to be. Now, even in this case, you should be able to see some kind of a distortion. So I think in the middle of this 8 versus in the middle of this 8, This is the one place where you can easily make out that there is a difference. But if I were to zoom out and show you, usually the one here, reconstruction with nonlinear activations, is going to be better than linear autoencoders across different layers. You can also quantify it by using MSE. So this is 0.067, while this is 0.003. So generally, that basically means that you should construct autoencoders with nonlinearities in between, which is pretty straightforward because throughout CNNs, we saw that it's essential to have these kind of nonlinearities within your architectures. Same thing exists within autoencoders as well. All right, so in terms of dimensionality reduction, so what we just saw was reconstruction. In terms of dimensionality reduction, fully connected autoencoders are helpful to us because one, they are unsupervised. They're also lossy. Now, you won't think that this is a strength, but hopefully at the end of today's lecture, when we discuss something called denoising autoencoders, you'll see that the fact that the reconstruction is not exactly the same is going to help you in denoising your original image. So these two can be considered as some kind of pros. The last one is, again, there's pros and cons to it. It's very data specific. So if you have trained your network with all these kind of number, the MNIST dataset image, you will not then be able to pass in something like this kind of a natural image and get back the output. So this will not happen with an autoencoder that has been trained on just MNIST images. In other words, it has overfit to the data that it has trained on. So there's no way that it can understand what a plane is going to look like based on the fact that it knows what a 3 is going to look like. So it needs to have an understanding, or you need to have trained it on some kind of natural images for it to actually reconstruct these natural images back. But the pro of being data specific is that you can do some kind of anomaly detection, which essentially means that we'll probably have a lecture on anomaly detection itself because it's very important. It tells you when a neural network should know when it doesn't know. It should know that it has only been trained on something like these numbers, which are 3, 4, 5. So whenever it is given an input of something like a plane, it should know that it doesn't know what to do. So it should tell you that, hey, I'm uncertain about this, so I will not be able to give you a good output in this particular case. So that's a very important framework that needs to happen. Like in ChatGPT, for instance, you give it a certain prompt, it always needs to give back a solution. But sometimes there are going to be instances where it does not know the answer. So the goal is that it should not hallucinate and tell you some incorrect solution. It needs to tell you that it does not know and ask for more information from you. So being able to do something like that requires this either uncertainty or anomaly detection process itself. So we'll discuss about that later down the line. So even though it's data specific, which is kind of a con, that fact we know that it is data specific can be used within an anomaly detection framework later on. All right. So then let's talk about the visualization process. So until this point, we have looked at these weights and looked at them as matrices, 128 cross 64, 64 cross 32. But there are some visual meanings that we can assign to these weights itself, and that is what we are calling as visualization, or at least that's the first part of the visualization process, which is visualizing the filters. And what I'll be discussing now is something that is again applicable to CNNs itself. We'll go back and look at CNN visualization as well, but in a larger context of explainability. So let's first visualize the filters, and then we'll come back to talking about visualizing the latent representation. So some mathematical notations. So you have a p-dimensional input, and there's about n of these inputs. Your W of k is your weights. These are just we can call them as weights, or we can call them as filters. You'll see why in a little bit, and this would probably be more clearer when we have when we show it in terms of CNN as well. So P in this case will be the number of neurons in a layer K, and P of k minus 1 will be the number of neurons in layer k minus 1, which basically means that if it's 128 cross 64, then 128 is going to be P of k. This is going to be P of k minus 1, while 64 is going to be P of k in this case. It's just number of neurons that exist within succeeding layers. So the goal for us is to extract the weights W of k and reshape into an array which makes sense to us, and then visualize it as an image, especially if you've trained it using images. In all cases, we won't take bias into consideration, because bias does not work directly on top of data. So it's not something that we are always interested in terms of explaining or understanding these neural networks. So let's say I have some kind of a grayscale image. I'm not sure why. So this is supposed to be something like a 3 or 5. Just think of it as some kind of a MNIST dataset image. Let's take the first layer. So the first input is going to be some kind of a 28 cross 28, which would be a 784 cross 1 vector. The next image, the next set of weights is going to be 128 kernels of 1 cross 28 cross 28. So in other words, we can think of this as a filter. Before we thought of this as a kernel, right? It's nothing more than a filter. It's just going through and filtering or convolve or doing some kind of an operation on top of your image. That's all it's doing. So we can consider that to be a kernel or a filter. And we look at that as this kind of a 1 cross 28 cross 28 as our input framework. Now this 128 essentially means that there are 128 sets of kernels. So again, going back to the CNN, this basically is nothing more than a convolutional layer with each height and width being 28 cross 28 and number of kernels being 128. Of course, right now we are discussing fully connected layer, but this is the way you would look at. We've already discussed that convolution layers can be used in order to construct these fully connected layers, right? So this is essentially something very similar to that. If I were to visualize a learned module, this is what the kernels would look like. So in total, each of them, let me just zoom into this. So this here is 28. This is 28. The number of pixels. So when I say 28 height, that means the number of pixels here are 28, and the number of pixels width is also 28. And in total, this multiplied by this, there are 128 such kernels or filters, and each filter has a size of 28 cross 28. You'll see a lot of these kind of visualizations if you open any paper on CNNs, or when we talk about explainability, you'll see a lot of these visualizations. All they're doing is just visualizing the weights in terms of images. Because these weights directly act on top of images, they are essentially nothing more than kernels. They're essentially nothing more than filters that directly operate on top of the images themselves, and you can visualize them in terms of images. Ideally, when you should be able to see that this should be something like a 5, there's something like a 3. There are better ways, there are better kernels that we'll see later down the line, but this is what you are going to see. I think when we first started with CNNs, we started with this idea of, I think it was Albert Einstein's image with the I being the kernel, right? We went through, convolved everything to see which had the highest number, and then we started doing pooling, where we said that the maximum value is achieved when the kernel and the image are overlapping each other. So that is exactly what is happening here. If the 5 overlaps the number 5, then that means that it should be a number 5. So you're just acting or operating on top of the image, and if the kernel is the same as the image, then that number is going to give you the highest activation. Of course, instead of this being a single layer, we have multiple layers here. That's why you won't see the exact number replicated here within the autoencoder here. Any question about what this diagram here refers to, the visualization here? All right, so we have two here. One is the linear one, and another one is the non-linear. It's not very easy to see the difference in these particular cases, but usually the non-linear ones are better in terms of the performance. But in terms of visualization, it's not always clear what they refer to. Now, this was just for the first layer, which is this one here. W1, 128 cross 1 cross 28 cross 28. But then we have two more sets of weights, right? This one, this one, this one, and this one. So these three things don't mean much in terms of visualizing the weights, because at this point, these visuals work for us. We can kind of make out 5 and 3 in these cases because it directly operates on top of images. But as soon as you come to the second layer here, all your points are scrambled. All your neurons are scrambled. Your spatial locality is not maintained within the second layer. The spatial locality is maintained within the first one because it's directly operating on top of the images. But on the second one, your first neuron is a combination of every other neurons within every other pixels within the image, right? So it doesn't mean much. Your second neuron also does not mean much spatially. So if I try to do the same thing where I construct this kind of filter sets and I visualize these filter sets, I don't see much here. It's just a bunch of pixels that are randomly assigned values. Doesn't matter if it's linear, doesn't matter if it's non-linear. Same thing in the next layer as well. The only takeaway is that as you go lower within your network, more neurons are activated. Like for instance, if I go back here, this entire filter seems that it's not being used because there's no template weight or some kind of a visualization that you can make out here, right? But when I come lower down the line, almost every single filter here has some kind of a unrecognizable pattern, but there is some kind of a pattern that exists within this framework. So that is my only takeaway, that more neurons are utilized when we go deeper, but in terms of visualization, it's not really as understandable. And this is a problem because one of the most important parts of autoencoders is this kind of a latent representation within the network. So we want to try to visualize and try to understand what is happening within the latent representation, but doing a very simple visualization of the filters is not going to help us. So that is when we have this kind of a dimensionality reduction thing that we need to do. Let's say you're given kind of a magic algorithm, something like PCA, for instance, where given a 32 cross 1 vector, you'll never be able to visualize a 32 cross 1 vector, right? So it's essentially just a vector of 32 numbers, and to do that, you need a 32-dimensional space. To visualize it like we do in a 3-dimensional space, we need 32 dimensions, and we cannot have that. So instead, what we need to do is convert this 32-dimensional vector into a 2-dimensional vector. So PCA helps us do dimensionality reduction. From 32 dimensions, we can go down to 2 dimensions. In this case, I think there are better algorithms than PCA. Tisney is probably the most important one that we use generally to try to understand representation space. And this should be available. I think on scikit-learn, PyTorch, Tisney is usually available. So given a vector of large, let's say 32 cross 1, you can then be asked to kind of convert it into a 2 cross 1 or a 3 cross 1, simple dimensionality reduction. And if you do that, this is how the output is going to look like within the 2-dimensional latent representation of MNIST. Right? You know MNIST dataset has about 10 numbers or 10 classes. So even without having access to the class labels, again, we have MNIST dataset, but we don't have the labels. We just have the images, the 28 cross 28 grayscale images. So given those images, we can convert them into this kind of latent representation space with different clusters being assigned in different ways. So this is how we would visualize 2D latent space. Of course, we can use PCA or Tisney in order to try to understand what is happening within the latent representation space. Again, all these, so for instance, green are 5s in this case, and the orange are going to be 7s, which is showing you that different classes are being clustered together. This is something, again, similar to what we saw in JMMs and K-means as well. It's just reiterating the fact that autoencoders are an unsupervised clustering approach towards data which where you do not have access to labels. We'll revisit this idea of visualization, both of the weights as well as the latent representation space, maybe next week. So some observations from latent representation space is, of course, weak discriminability. So these are not discriminative. Autoencoders are not discriminative algorithms, where you're not by discriminative algorithm, I mean they are something that is used in order to classify images. So you're not going to be classifying images based on autoencoders, but if you look at the latent representation space, there is weak discriminability. Of course, there is this kind of a light blue cluster that is not as well represented within the dimensionality space itself in this visualization, but still you can see that there is some kind of a discriminability within the network. There's also a discontinuity. The digit-like image decoded from gap regions look unrealistic. Gap regions essentially means these regions here, or some kind of images that may be digit-like, but when you actually do the decoding part or reconstructing it, they don't actually look like any of the images that you have trained on. Images are slightly harder, but if you try to do something like document categories, you will see that it's much easier to do this kind of 2D latent representation and discriminability on these kind of tabular data sets, where you'll be able to classify them based on different topics and what the documents are. All right, so that was for fully connected autoencoders. Any questions about fully connected autoencoders before we move on to convolutional ones? Yes?
Since there aren't any labels with the autoencoders, when we're looking at these graphs, what are those labels based on?
Oh, so in this particular graph, we just made it easy so that we can understand what is happening. We put it in terms of the classes itself. So if you were to do it without the colors, that is what the representation space would look like. But for it to make sense, we added orange color for 7 and green color for 5 and so on.
So like, let's say with the document one, if you had all these documents, would you have to go in and label all of them to have this graph?
Not really. So similar to K-means clustering, right? If you had the centroid, if you label the centroid, then that means any of the elements associated with that centroid would be labeled the same as the centroid. Similar thing here as well. Choose one of the elements which has all greens, or choose one of the elements which has all these same representations and label that. So instead of labeling 10,000, so in this, for instance, there's about 60,000 images here. So instead, if you just label 10 images, you'll be able to get this kind of a cluster setup. Again, labeling is a very manual task. It's not easy. Doing it on these kind of images is fine, but then you worked on SAM prompting and getting some of the results, right? So that was not easy. It's a very manual, hard process. So instead of that, if you had SAM do the clustering, and then instead of you going on 400 and doing it yourself, rather it showed you, hey, tell me what the class of this is going to be. If it shows you something as its centroid, then you can take that and help the labeling process itself. So it's something very similar to that, where you don't have to spend as much time labeling. Once you do the clustering part, you can go through and then organize it yourself. All right, so what we saw was convolutional autoencoders, and the natural transition now is going to be for, what you saw was fully connected autoencoders, and the natural transition now is going to be for convolutional autoencoders. Very similar to what we did before with fully connected networks in classification and then CNNs. It's going to be the same thing here as well. And the methodologies and the motivations are going to be similar. We want to preserve some kind of spatial locality, and we want to share weights between all these localities. So we want to be able to use convolution kernels within our encoder-decoder setup. So the encoder is going to be exactly the same as our CNNs. We have these kind of, even the visualizations that you're seeing here are very much similar. So whenever you have these kind of cuboids, the height, you have width, and you have number of channels, right? Exactly the same as before. So you have a 784 cross 1, or maybe here I should say it's a 28 cross 1. So you then have, I don't know, 3 cross 3 kernels and 64 channels, and then 5 cross 5 kernels and 32 channels, and so on. So until this point, it is going to be the same as a CNN, where you'll have convolution with stride, and then you'll have convolution with pooling as well, where you're reducing the size of your images and your features. But after this point, you need to start with your decoder. And your decoder architecture needs to have some kind of an unpooling plus convolution. So convolution is something that you have seen before, but unpooling is not. We had pooling before, right? Whenever you had max pooling, that basically meant that we chose the number with the highest value and assigned that for the next step. But unpooling is the opposite of that, and that is what we are going to be talking about today. And this idea, or you can think of this as transposed convolution with stride. The only difference here is that you're actually learning this convolution as well. So it's not just VK transpose. It is not that. In other words, it's not that you have learned these convolutions here and you're just transposing this convolution here. You're actually learning a new set of parameters later down the line as well within this particular setup. And so a lot of you are actually using unit architectures within your project setup. It's very similar to this, except of course you're not reconstructing the input, you're reconstructing the ground truth that you have, or your segmented masks, but the architecture itself is very similar to this, where you'll have some kind of convolution kernels and unpooling and upsampling layers throughout your framework. So let's talk about what unpooling is. So some of the simplest unpooling is going to be this nearest neighbor and bed of nails, where given you know that, let's say your input is 2 cross 2, and you know that after unpooling, your output needs to be 4 cross 4. So the easiest thing you can do is take 1 and propagate it to this kind of a 2 cross 2 framework. Take 2 and propagate it to this 2 cross 2 framework. 3 here, and 4 here. So given that there is some kind of a stride, we'll talk about what that stride is later down the line, but given that there is some kind of a stride where you want to go from 2 cross 2 to 4 cross 4, all you're doing is just replicating the numbers that you have within your outputs. So what this means, by the way, is that at this stage, let's say at this stage, if you had 1, 2, 3, 4, and at the next stage, if you wanted to convert it into a 4 cross 4 thing, this is what it would look like if you're using nearest neighbors, and this is what it would look like if you're using bed of nails. Bed of nails, of course, is that you have a fixed location. Say you say that your whatever element is here needs to go in the top left corner, and then you just zero pad all the other ones. So there's going to be a 0 here, here, here. And of course, you can choose, by the way. You can say that your 1 can be at the bottom right corner. So this could have been a 1, in which case this would have been a 0. And same thing here as well. This would have been 2 here and 0 here. But essentially, you're just moving that 2 that you had to this position here, and all the remaining ones is going to be 0. So it's the exact opposite of pooling, except in pooling you were just discarding all the other values. Now you in fact have to add these kind of values, and this is where the choice comes in. Do you want to replicate your nearest neighbors, or do you just want to zero pad and say let's make it 0? So these are 2 different strategies that we can use, and these are very simplistic strategies. The more common ones are something like max pooling with indices. In other words, what happens is that you have these kind of pooling strategies, right? So this is pooling within your encoder. It's doing a 2 cross 2 pooling, which means 1, 2, 3, 5. Your 5 is the maximum in this 2 cross 2 framework. So you are going to move this here. The additional thing that you're going to do is you are going to note down what the index of this value is going to be. So this index here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, this is 10, 11, 12, 13, 14, and 15. So these are the indices. Within my 4x4 input, I have these indices. And not only are you going to remember the pooling part, which is you're going to remember that 5 is a max here, you'll also remember this index. In the next one, it's 6 at an index 2. The bottom here, it's 7 at an index 12. And then here it's 8 at an index 15. So this is something additional that you need to do within your encoding architecture itself, where you remember what the index needs to be. And then while decoding, you can put that element, let's say the 5 element, at the 5th index. So you know that 5 is going to exist here, 6 is going to exist here, 7 here, and 8 here. Sorry, this is incorrect. This should have been a 0. You don't know that 4 exists there. So this should have been a 0. So this is one of the most commonly used unpooling methods or upsampling methods, max unpooling with indices. So there's an additional step that you would have to do within your encoder in order to create this kind of a decoder architecture. All right, yes?
Why do we choose 0 for the padding versus like a random value less than the max value?
Can you repeat that?
Why is 0 chosen to fill in the gaps versus some kind of like random distribution less than the max value?
So 0 is not usually chosen. It's just 0 padding is something that we generally use. What usually happens is that in these methodologies, in the middle, you'll have like batch norm methods, right? So you'll have batch norm layers, and batch norm layers generally calculate the mean. So at this point, you'll know what the mean needs to be. So generally, you'll add mean at the stages. But again, these are new things that have come out these days. Originally, when we had unpooling start, this is when 0 padding was probably the most common. And we used to use just add zeros over there. But it's not the most commonly used right now. But we are learning about it because, again, traditionally this is how it started, so it's important to know where it's coming from. Everything usually comes from the 0 padding methodologies within convolution. All right, then let's discuss about the idea of stride. So in all these cases, we really did not consider stride a lot, but maybe stride is something that is going to be important. So at this stage, our stride was 2. But let's say that our stride is going to be 1, right? That means that I need to take this 2x2, and if I have a 3x3 kernel, I know that I need a 3x3 kernel, then that means that I need to act on this part of the image, and I will need to act on this part of the image. And after convolution, I'll get something like this as my output. So this was only the max unpooling part. So this is now decoded with the convolution part as well. So this is how a convolution is going to act based on the fact that we know that our unpooling is done. So the next few slides go through this kind of a methodology. So 2x2 transpose convolution, stride 2. We learn unpooling plus convolution. So 1, let's just say we're using some kind of a nearest neighbor approach, the easiest approach in order to get all these 1s. If I'm using 2, then I'm getting 2s here, 3s, and 4s. So the first part within our framework is going to be unpooling. This is opposite of the encoder, right? In encoder, we had convolution first, and then we used to do pooling. In the decoder, it's the opposite. We first do an unpooling, where we take this kind of a 1, 2, 3, 4, and then convert it into all these unpooled, a larger 4x4 method. Now, look at this filter. We had a 2x2 filter of all 1s. That really does not change the equation as much. But let's say I give you a different kind of kernel, which is 0, 1, 2, and 3. This is where the difference starts coming in. When you have 0 as your input, it really doesn't matter what your kernel is going to be. You're always going to get all zeros. But let's say I have 1 as my kernel here, the value of my kernel here. You're going to multiply your input 0 into 1, 1 into 1, 2 into 1, and 3 into 1, and place it here. And if you have 2 as your kernel, again, this is your convolutional kernels. And at this point, I'm just saying that, let's say you have learned this convolution kernel or you're given this convolution kernel, then this is how your output is going to look like. So if it's 0, 1, 2, 3, and your input is going to be 2, so basically this is 0 into 2, 1 into 2, 2 into 2, and 3 into 2. This is 0, 2, 4, and 6. And finally, if your kernel is 3 for this input, then 0 into 3, 1 into 3, 2 into 3, and 3 into 3. So that is how you get 0, 3, 6, and 9. So this is a combination of convolution and pooling that we are currently doing. Instead of just doing pooling separately and convolution separately, we're just multiplying and adding everything. And the addition part is going to give you this. You're just adding at every element what the values are. 0, 0, 0, 0. So it's always going to be 0. Here it's 0, 0. If there's nothing, you're just going to be adding zeros here. So at all these instances, it is going to be zeros. And all you're doing is adding. And if you do that, you get this as your output. So this essentially is how we do some kind of an unpooling plus a convolution strategy. So unpooling is just increasing the size of your kernels, and then convolution is you're adding on top of it. If you were simply doing a convolution without the unpooling part, then there won't be zeros here. You'll just be adding the 0, 0, 0, 0 with the 0, 1, 2, 3. This is how you already did convolution last time within the encoder part. But now, because of the unpooling, you're increasing the size and then adding them all together. Is this clear how we are doing this kind of a transpose? This is what we call a transpose convolution with some kind of unpooling and stride. Of course, so there is some kind of a padding that has been added. So all these things here, all these zeros have been padded on top, right? Because you know at the end of the day, you'll be adding all these elements that are at different spatial locations. So you need to pad all these elements. So there's this kind of an implicit padding that needs to happen on the output itself. So if we have some kind of a stride, so stride 2, then that means the second one will be here rather than being here. This is what we saw previously, but there's an additional extra step. So exactly similar to what we had before within the normal convolution setup. This is going to be the same as well, where there'll be an extra stride that we need to take into consideration. Same thing on the right-hand side. This is at the bottom left and bottom right as well. You will have all these elements that you would have to take into consideration when doing convolution. And similar to before, we'll have an output size, which is based on this formula, where, again, it's the exact opposite. So you'll have a very similar framework in this case as well. Any questions about the decoder architecture itself? It'll help if you just go through the slides once again, just to try to understand and work it out yourself, the unpooling part as well as the convolution on the decoder side. Convolution is exactly the same. It's just adding that unpooling layer adds this kind of an additional computational step where you need to do padding in the middle and then add it. Usually convolution is multiplication plus addition, but right now it's multiplication plus padding and then addition in order to get your outputs. That's the major difference that exists between the encoding and decoding layers. So if I were to construct a convolution autoencoder on MNIST dataset, this is what I have used in terms of getting the results that I'm going to be showing you. You'll still have the same kind of images, and ideally you want a reconstructed version of that images. I'll be using ReLUs for all my activations, but at the very end, of course, again, similar to what I had mentioned before, I'll use a sigmoid as my nonlinearity, and these are my results. So this is about 50% better than before. 0.036 is better than 0.006, and then I have 0.01 in my convolution autoencoder. That is going to be even better than my fully connected autoencoders, at least in terms of the quantitative numbers as well. And you can probably make out the difference. Actually, I don't know if it's clear. Yeah, maybe the 6 is a little bit clearer, right? It's sharper at least. When I mean clear, I mean it's sharper at least. So you'll be able to see, at least visually, that your convolution autoencoders generally gives better results than a fully connected autoencoder. All right, with that, we would go to the regularized and variational autoencoders, but I think we are out of time for today. So we'll discuss that on Wednesday, along with the exam questions as well, or the solutions for that as well. Again, no office hours today after class.
Oh.